All right, discrete math. We are in our third lesson for chapter 2. I'm talking about the mathematics of power. We just got done talking about Banzhaf power. We're now going to talk in section 2.3 about what's called Shapley-Shebik power. So a different approach to measuring power that was first introduced by the American mathematician Lloyd Shapley and economist Martin Shubik in 1952. The key difference between the Shapley-Shebik measure of power and the Banzhaf measure of power centers on the concept of a sequential coalition. So if you recall coalitions, we originally talked about it did not matter that the order that you wrote them in. In the Shapley-Shebik method, the assumption is that the coalitions are formed sequentially instead. So players join the coalition and cast their votes in an ordered sequence. There's a first player, then comes a second, then a third, and so on. Thus, to an already complicated situation, we're adding one more little wrinkle. The question of the order in which the players join the coalition. So let's look at this in a three-player sequential coalition. When we think of the coalition involving three players, P1, P2, and P3, we think in terms of a set. For convenience, we write the set as P1, P2, P3, but we can also write it in other ways, such as P3, T1, P2, P3, P1, and so on. In a coalition, the only thing that matters is who are the members. The order of which we list them is irrelevant. But in a sequential coalition, the order of the players does matter. There is a first player, a second player, and so on. So for three players, P1, P2, and P3, we can actually form 6 different sequential coalitions. P is the first player, the P joined in, and then last came P3 as shown on the next slide. So your sequential coalitions, here those are P1, P2, P3, P1, P3, P2, P2, P1, P3, and so on. You can actually get that using factorials that we introduced, I believe, back in the previous chapter, which is that if there were a total of 3 players that are involved, then for the first one you have 3 choices. The second one you would have 2 choices left. The third one you only have 1 choice left. And 3 multiplied by 2 multiplied by 1 is 6. Another way we wrote that was as 3 factorial equals 6. So a little bit of math behind why that is. So in the Shapley-Shebik approach, there's a pivotal player. So in every sequential coalition, there's a player who contributes the votes that turn what was a losing coalition into a winning one. We're going to call that player the pivotal player of the sequential coalition. Every sequential coalition has one and only one pivotal player. To find that, we just add the players' weights from left to right one at a time until the tally is bigger or equal to the quota. The player whose votes tip the scales is going to be the pivotal player. So the Shapley-Shebik power index for a given player P, the Shapley-Shebik power index of P is obtained by counting the number of times P is a pivotal player and dividing this number by the total number of times that all players are pivotal. The Shapley-Shebik power index of a player can be thought of as a measure of the size of that player's slice of the power pie, and it can be expressed either as a fraction between 0 and 1 or as a percent between 0 and 100%. So the Shapley-Shebik power index, we're going to use this notation of sigma 1 to denote the Shapley-Shebik power index of player 1, sigma sub 2 to denote the Shapley-Shebik power index of P2, and so on. So the Shapley-Shebik power distribution, if you look at the complete listing of all of the Shapley-Shebik power indices of all the players, is going to be called the Shapley-Shebik power distribution of the weighted voting system. It tells the complete story of how Shapley-Shebik power pie is divided among the players. So here's a summary of the steps to computing the Shapley-Shebik power distribution. Step 1, you're going to make a list of all the players of all the possible sequential coalitions of the n players. We're going to let T be the number of such coalitions. We'll have a lot more to say about T soon. In each sequential coalition, determine the pivotal player. For bookkeeping purposes, we're going to underline the pivotal players. And then count the total number of times that P1 is pivotal. This gives S sub 1, the pivotal count for P1. repeat for each of the pivotal players to find SS2, SS3, all the way up to SSN. We're then going to find the ratio, sigma 1 of SS1 over T. That's going to give the Shapley-Shebik power index of P1. We're going to repeat that for all of the players from sigma 2 all the way up to sigma n. The complete list of sigmas will give us the Shapley-Shebik power index or power distribution of the weighted voting system. Don't forget about the multiplication rule. It's one of the most useful rules of our basic mathematics we're going to be doing, which is that if there are n different ways to do x and n different ways to do y, then to do x and y together, you can do that by taking m by n different ways. All right, so Bigger Ice Cream Shop offers 5 different choices of cones, 31 different flavors of ice cream. It's not a boutique ice cream shop, and 8 different choices of topping. The question is, if you're going to choose a cone and a single scoop of ice cream, but then add a topping for good measure, how many different orders are possible? So that rule of multiplication says that if you take 5 multiplied by 31 multiplied by 8, I believe, let's see, 5 multiplied by 8 is 40, multiplied by 31 would be 120, would be let's see, let me put that in a calculator real quick before I make an easy mistake. 40 multiplied by 31 is 1,240. So quite a few different combinations of ice cream. So the number of choices, too large to list individually, obviously. We can find it using the multiplication rule twice, which is what I just showed. They went ahead and multiplied 5 and 31 together first. I did 5 times 8 first, but hey, we still end up getting the exact same thing, which is the 1,240 different cone flavor and topping combinations. So, how do we count the number of sequential coalitions with 4 players? Using the multiplication rule, we can argue as follows. We can choose any one of the 4 players to go first, then choose any of the 3 remaining to go second, and any of the 2 remaining to go third, and finally, the 1 player left goes last. So using the multiplication rule, like I mentioned in a previous slide, you would take 4 multiplied by 3 by 2 by 1 is 24, which is the same as taking 4 factorial. So if we have 5 players, following up on our previous argument, we can now count on a total of 5 multiplied by 4 by 3 by 2 by 1 is 120 sequential coalitions. And within players, the number of sequential coalitions is always going to be given by n multiplied by n minus 1 all the way down to 3 times 2 times 1, which is again called the factorial of n, and is written in shorthand form in factorial. All right, so that's going to give us our number of sequential coalitions. Let's go back. Let's revisit an example, 2.10, which was talking about the NBA draft. The weighted voting system there was 6 as our quota, and then 4, 3, 2, 1. We're now going to find its Shapley-Shebik power distribution. The table on the following slide is going to show the 24 sequential coalitions of P1, 2, 3, and 4. And again, the 24 coming from 4 factorial. In each sequential coalition, pivotal player is underlined. So each column corresponds to the sequential coalitions with a given first player. So you can see where you've got P2 is our pivotal player here, P3, P2, P3, P1, P1, P4, P1, and so on. So your total counts for player 1, there were 10 moments where they were the pivotal player. For player 2, there were 6. Player 3, there were 6. And player 4, there were 2. So then the Shapley-Shebik power distribution is given by the following. Sigma of 1, you take the 10 times that they were influential, that they were pivotal, divided by the 24 total possible is 41 and 2/3. For player number 2, 6 divided by 24 is 25%. That would have been the same for player 3. And sigma 4 for player 4, 2 out of 24 is 8 1/3%, so 8.3%. If you compare this result with the Banzhaf power and distribution that we got from the previous lesson, you're going to notice that the 2 distributions are actually the same. If nothing else, this is going to show that it's not possible for Banzhaf and Shapley-Shebik power distributions to agree. In general, however, for randomly chosen real-life situations, it is very likely that Banzhaf and Shapley-Shebik methods will give the same answer. Uh, so that's what we've got for Shapley-Shebik. Moving forward into section 2.4. 2.4 is less to do with the actual weighted voting itself. It more just has to do with the idea of what are called subsets and permutations, which are some more of the math stuff behind the weighted voting that we've been talking about. So that being said, guys, have a good rest of your day. I'll talk to you next time.